Hello, I am Alejandro Gomez Yepes from the University of Vigo, and I'm going to present the paper General Open-Phase Fault-Tolerant Online Current Reference Generation for Maximum Torque Range and Minimum Copper Loss with Phase Current Peak Limitation for M-Phase PMSMs with non-sinusoidal Back-EMF. And this paper is the result of a collaboration between the University of Vigo, the Alexandria University, the Arab Academy of Science and Technology of Maritime Transport, and the King Abdullah University of Science and Technology. So here we have the acronyms that we use to the paper. And now let's review briefly the state of the art on this subject. So multi-phase PMSMs with non-sinusoidal like EMF offer high fault tolerance and torque density. And here we have a scheme that depicts a multi-phase drive of any number of phases. We have a closed loop current controller. And for this controller, we have the references for the phase currents IK. And in this block, we generate these current references, which are obtained based on the position of the rotor, as well as on the torque reference, which may be generated, for example, by an outer speed control loop. So this block, the current reference generation, is crucial. There are several methods that exist in the available literature, and most of them either minimize the stator copper loss, which may be called maximum torque per RMS current, or some other are aimed at maximizing the torque range, which often is known as maximum torque per peak current. On the other hand, the full torque range minimal loss methods are able to actually achieve both goals simultaneously, but so far they are only suitable for sinusoidal back EMF, not for these PMSMs with harmonics in the back EMF. And also, many of the methods of current reference generation are all, not general, but only suitable for some cases like healthy drive or specific machine types, like, for example, specific phase numbers or specific back EMF harmonics or just certain open phase fault scenarios. So in order to overcome these limitations, this paper proposes a novel method of current reference generation for multi-phase PMSMs that is general for any number of phases, any back EMF harmonics, and for either healthy or faulty case with any possible open phase fault scenario. When the torque can be achieved without surpassing the rated peak current, then it ensures minimum losses per torque value. And at the same time, the torque range that can be achieved without torque ripple is maximized. So this means that we actually have a full torque range minimal loss method, like the existing ones for sinusoidal back EMF, but in this case, it's also suitable for non-sinusoidal back EMF. In case the torque reference T is very large and cannot be achieved without torque ripple, then this method provides this high torque while minimizing the instantaneous deviation from the torque reference, which means that the torque ripple is minimized for a given high torque reference. For discussing the proposed method, first we have to review a previous method that is very popular for PMSMs with non-sinusoidal back EMF, which is the method proposed, for example, in this 2011 paper by Shawier and Eric, where they propose the current references for minimum copper losses per torque without taking into account the current limit. So it can be considered as a conventional method based on maximum torque per RMS current. Reference currents are obtained as a solution of this optimization problem based on the method of the Lagrange multipliers. So this optimization problem tries to minimize this construction, which is defined as the copper losses, the sum of the squared phase currents, subject to two constraints. One of them imposes the desired torque reference, so the sum of the product of the back EMFs and the phase currents. And on the other hand, the sum of the phase currents has to be equal to zero because we are assuming that we have a single isolated neutral point. So if we solve this optimization problem offline, we obtain this formula that we can implement online in order to obtain the minimum copper losses per torque, where E is the vector of the phase back EMFs. F is a vector that has 1 in the places corresponding to the healthy phases and 0 in the places corresponding to the phases that are open. And this dot is the element-wise product between pairs of vectors. So these are the optimum currents for minimal losses per torque without taking into account the current limitations. We can see that all phase currents increase linearly with the torque reference. So as soon as one of the phase currents reaches the maximum peak current, then T cannot be increased anymore. That's the maximum torque that can be achieved with this method. And this is illustrated, for example, in this figure. So the dashed dotted lines represent a torque reference of 75 newton meters. And we can see that at least one of the phases reaches the maximum that is indicated as 1 per unit because it's normalized by the maximum peak current. And if we keep increasing the torque reference up to 100 Newton meters, as represented by the solid waveforms, we can see that since all the phase currents increase linearly, there are some parts where the phase currents are greater than the maximum limit. So we have overcurrent, and it cannot be tolerated by the drive. So the maximum torque that we can achieve is, in this case, 75 Newton meters, so that none of the phase currents exceeds the limit. So this is an important drawback of this method, because the maximum torque is reduced by this fact. And now let's explain the proposed method of current reference generation that will achieve minimum copper losses per torque while respecting the peak current limit of the drive usually imposed by the switches. And this is different from the previous method where this limit was not taken into account. And in this case, this will imply that we are not only minimizing the copper losses per torque, but also maximizing the torque range that can be achieved without torque ripple. And also this method will consider the case where the torque reference is even higher, so that torque ripple is unavoidable. But in that case, the instantaneous torque deviation from the reference will be minimized, which means that we are minimizing the torque ripple. So for this purpose, so let's first analyze the case of where T can be achieved while respecting the limit. And what we do is that we take the same optimization problem as in the previous method, but we modify a couple of things. So in this case, even though we are still minimizing the copper losses per torque as a cost function, instead of considering all the healthy phase currents as variables, we split the healthy phase currents among those that are regarded as variables, IV, which are those that are within the peak current limits. And also we have some non-variable currents, IMV, which are saturated to the maximum peak current because otherwise they would tend to surpass it for a given torque reference. Then if we solve this optimization problem with the constraints and the cost function of the previous section, then we obtain this formula which is more general than in the previous method. And in this manner, if we run this online during the execution, you obtain for each control sample the variable currents as a function of course, the torque reference and the Back-EMF, but also as a function of the IMV currents, which are equal to the peak current limit because they are saturated, and also the vectors FV and FMV, which are defined here. So they have FV has ones for each of the phases where the current is considered as variable, and FNV has one for each of the phases where the current is saturated to the limit. The other elements of these two F vectors are set to 0. So in this manner, we have minimum copper losses per torque while respecting the limit in the phases where the phase current would otherwise tend to surpass this limit. So we will obtain higher torque than in the previous method while obtaining minimum copper loss for each torque value. So this equation will be used online when the torque reference can be actually achieved without surpassing the peak current in any phase. Let's see now the entire scheme of the complete method here. So this block diagram describes the entire proposed method for generating the optimum current references for each of the control sample for the input torque reference. So in the first place, we assume that all the healthy phase currents are considered as variables, as degrees of freedom. And we also assumed initially that the torque reference can be achieved without exceeding the maximum peak current. Then we compute the variable phase currents, which in this case, as we said, are equal to all the healthy phase currents, in order to obtain the torque reference with minimum copper loss, which can be with either the equation of the 2011 paper or the new equation that we have just proposed for the variable phase currents. Because in this particular case, when all the healthy phase currents are variable, those two equations are exactly the same. And now we enter this loop where we can perform several iterations. So in each iteration, basically, we check if any of the phase currents exceeds the maximum peak current. And in such a case, we reduce the number of variable currents by setting the corresponding current to the maximum peak current so that it's no longer a variable current, it's a non-variable current. And we have saturated it to the maximum peak current. And then we compute again the variable phase currents to obtain the reference torque with minimum copper loss by using the equation that we just shown, which in this case is no longer equal to the one of the 2011 paper because of the fact that we have non-variable currents. Here we check if three conditions are are met simultaneously. So if any of these three conditions is not met, then we would leave the iteration loop. So we check if the solution obtained for the variable phase currents is real, because if no proper solution is found, then it means that the torque reference is unfeasible. It cannot be achieved while respecting the peak current limits. Another condition that we check is if any of the phases surpasses the peak current, because if they don't, then it means that the torque reference T is actually achieved. So we have a solution that we can use to obtain the torque reference with minimum copper loss while respecting the peak current in all phases. And another thing that we check is whether there are at least two variable phase currents that are below the maximum peak current. Because otherwise, if there are not at least two variable degrees of freedom in the phase current, there are not enough degrees of freedom that we can saturate in the next step in order to see if the torque reference can be achieved. So in that case, we would also conclude that the T torque reference is unfeasible. It cannot be achieved while respecting the peak current. And in the next decision, we have to distinguish whether the torque T has been achieved or it is unfeasible. So here, what we check actually is, again, the second and third conditions of the previous decision, so that we can distinguish between these two cases. So if we conclude that the obtained current references are actually enough to provide the torque reference T, then we simply add the variable and non-variable currents so that we generate finally the desired phase current references. Otherwise, if we conclude that T is unfeasible, that it cannot be achieved while respecting the maximum peak current, then what we do is that the torque deviation, which is unavoidable, is minimized. And this is done by setting the phase currents to the maximum peak current in as many phases as possible with the sign of the corresponding phase back EMFs. There are some phases where this might not be possible because of the fact that we also have to consider the constraint that the zero sequence current is zero, because we are assuming that there's a single isolated neutral point. So if not all the phase current can be set to the maximum peak current with the sign of the back EMF, then it will be set at least in the phases that have the largest magnitude of the phase back EMF, and then we set the phase current reference accordingly. So now let's apply this proposed method to the example of a 5-phase PMSM with one open phase fault in phase A. This is the same example that we have used to check the existing method of 2011 here, where we saw that the dash dot waveforms, which correspond to 75 Newton meters, are the case of the maximum torque that can be achieved with this conventional method, because one of the phase currents achieved the maximum peak current of 1 per unit. And if we increase the torque, there will be overcurrent. So if we compare that with what we obtain now for a torque reference that is higher than that, it's 80 Newton meters instead of 75 Newton meters. And we can see that in this case, there's no overcurrent in any of the phases. The maximum peak current is respected in all of the phases at every single time, because the proposed method effectively saturates to 1 per unit to the maximum peak current all the phases when they would otherwise exceed the limit. So the method works properly, and also the torque is smooth. So it is feasible to obtain the torque reference at all times. And hence we can conclude that we have been able to increase the torque range without torque ripple compared with the previous method of minimal losses. And now if we further increase the torque up to as much as 100 Newton meters, then we can see that there are some samples where the torque reference can still be achieved, like this vertical line. And there are some other cases when it is not possible because all the phase currents are saturated to the limit. And in that case, the method is still effective in preventing overcurrent because the current is still respecting the limit, but there is some deviation of the final torque TF from the torque reference, but this deviation is minimized, and hence the torque ripple is also minimized. So we have been able to keep increasing the shift torque even beyond the maximum ripple-free torque. And next, we will show the experimental results, which were obtained with a 6-phase PMSM with asymmetrical winding arrangement and one open phase fault. So here we can see the back EMF waveforms, where we can see that they are nearly trapezoidal for higher torque density. And in this case, first we test the case where the torque reference is equal to the maximum provided by the conventional method of the minimal losses, that is the maximum torque per RMS current from the 2011 paper. And effectively, we can see here that there's one of the phase currents that reaches the limit of 1 pu. So the torque cannot be increased anymore with the conventional method. The torque is achieved, but it cannot be increased anymore. And this is the experimental torque. Yeah, it's a bit different from the torque reference and from the final torque that corresponds to the current references, TF. This is normal because the current controller that we are using is a model relative control, which is well known to have steady state error. So it's not unexpected to have a different experimental torque. It could be corrected by using, for example, observers, but it's beyond the scope of the paper, which is focused on the generation of the current references. We can see anyway that the currents followed to a reasonable extent the current references as well. So now let's keep increasing the torque reference. So now we increase the torque from 8.8 up to 11.2, which represents the maximum torque that can be set without exceeding the RMS current in any phase. Of course, this is achieved by using the proposed method because the conventional method was not able to surpass 8.8, which we called torque T1. And here we can see that we can effectively increase the torque reference without exceeding 1 per unit in any of the phases. So the integrity of the drive is effectively preserved. It is important to remark that this torque reference T2 of 11.2 Newton meters is defined as the maximum torque without exceeding the rated RMS current of the machine in any phase. But since the thermal dynamics of an electric machine are very slow, it can be considered that this T2 torque is only the maximum at steady state, because during transients we can actually surpass this torque reference as long as we don't exceed the instantaneous maximum peak current, which is typically that of the converter switches. So during overload, we can increase this torque reference from T2 to T3, which is about 11.8 Newton meters, and is of course even greater than the maximum torque of the conventional method. So this torque reference of 11.8 Newton meters provides a torque, a final torque TF associated with the current references that is smooth and equal to the torque reference. There is no ripple in the reference torque. Of course, in the actual experimental torque, there is some unavoidable ripple, but it's still relatively smooth. We can keep increasing the torque reference beyond T3, but then there will be some torque ripple, which is unavoidable. Also in the signal TF associated with the final current references. And also the experimental torque shows some higher ripple at those points, analogously to the final torque TF of the current references. And this is because at those times it is no longer possible to achieve the torque reference without exceeding the instantaneous peak current in some phases. So what the method does is that it saturates all the phase currents to the maximum instantaneous peak current 1 pu in a manner such that the ripple is minimized. And still there are applications where this could be acceptable during overload during transients. Now let's see the curves of the state torque copper loss versus torque reference T. And here we compare several methods. So the red circles correspond with the conventional methods from the 2011 paper, the maximum torque per RMS current, which provides minimum losses per torque, but only up to a maximum torque of 8.8 Newton meters. So the proposed full torque range minimum loss method that is also general, it's able to extend the maximum ripple-free torque range because the torque can be increased while keeping minimum losses per torque up to a maximum ripple-free torque of 11.8 Newton meters, and then we can keep increasing the torque even though there are some minimum torque ripple. So this is summarized here. We have provided minimal losses per torque, and also compared with the 2011 conventional minimal loss method, we maximize the ripple-free torque range, which is during overload, it can be increased up to 34% compared with T1. But in steady state, it's still increased by 26% with respect to T1, because this is the case where we're doing transients, we're exceeding the RMS current that is rated for the machine in some phases. And in steady state, we are also respecting not only the instantaneous peak current of the switches, but also the rated current of the machine in steady state. But in both cases, the increase in ripple free torque range is great. And actually, also if we allow torque ripple, then the torque the mean torque is even greater. And also we are comparing here with the maximum torque per peak method. But even though in available literature there are several maximum torque per peak methods, they are not general, and actually there are no methods in the literature that are suitable for this kind of machine in under an open phase fault like we are testing here. So what we do is that we obtain an equivalent maximum torque per peak method. It is based on the current waveforms provided by the proposed method, and then they just rescale these current waveforms with the torque value, so that the waveform is the same, just rescaled. But in this manner, the copper losses per torque are not minimized. So it's clearly worse than the proposal in terms of efficiency. Now, finally, we will summarize the main conclusions of this paper. So in this paper, we have proposed a novel method for generating online the current references for fault-tolerant end-phase PMSMs. So the method, when the torque reference T is not too high, if it's feasible without exceeding the maximum peak current in any of the phases, then it provides minimum stator copper losses per torque, and at the same time, it maximizes the ripple-free torque range that can be achieved, combining both goals at the same time. So it can be considered as a more general kind of full torque range minimal loss method. In case the torque reference is too high, so that it is unfeasible without exceeding the maximum peak current in any of the phases, then in such a case, the method provides minimum deviation at every instant from the torque reference, which means that the torque ripple is minimized. And it is very important to remark also that the proposed method is general for either symmetrical or asymmetrical windings. It is also general for any phase numbers. It is suitable for either healthy case or open phase fault with faults in any of the phases. It is also suitable for any kind of Back-EMF waveforms, which means that it can be used for any Back-EMF harmonics. And as a particular case, of course, since because of this generality, it is also suitable for the case of PMSMs with sinusoidal Back-EMF as a particular case. We have also concluded that the torque range is substantially extended, not only during a steady state, but also during transient overload by increasing the RMS current beyond rated in some phases while respecting the maximum instantaneous peak current. So the fact that it is also suitable for transient overload makes it particularly suitable for some applications where this property is of great importance, like for example in electric vehicles where it is required for some cases like overtaking, emergency braking, steep slopes, or other cases. And we have also to acknowledge that this method increases to some extent the complexity compared with the conventional method, but this increase is still acceptable in order to execute the method in its sample. Also, you may find a Simulink model for download that we have uploaded to the internet. You may find the link, for example, in ResearchGate and also in LinkedIn. Moreover, you may also find further work from our team on understanding this method, because it has been already accepted for publication in Transactions on Transportation Electrification in a new paper that is available already, although it will be published during the next months. Thank you very much for your attention.